Yeah, thank you so much for the introduction. I'm Robert, and today I'm going to be talking about learning theory in the quantum universe. So this is going to be a tutorial talk, and I wanted to make it more interactive and informal. So feel free to ask questions just during the talk. And some part of the talk, I'll be using the Blackboard here and try to write as big as I can. But let me know if I'm writing too small. And yeah, let's get started. So as we all know, a central goal of science is to learn how our universe operates. And since our universe is inherently quantum mechanical, the ability to efficiently learn in the quantum universe can lead to many scientific advances. For example, if one can efficiently predict how a collection of molecules will interact with one another and do interesting reaction, if we can efficiently make predictions about such quantum many-body systems, it can potentially lead to advancement in catalysts and pharmaceutics. On the other hand, if one can efficiently extract and learn properties about some exotic quantum matter, that can also lead to new insights that can impact condensed matter physics and material science. But more excitingly, being able to learn about quantum systems can help us better understand, better engineer, and better control quantum devices for all kinds of purposes, from doing computation to sensing to doing communication, etc. So as we can see from all of these applications, if we would really want to accelerate in the development of quantum science, it's very important to understand how we can efficiently learn about them, understand them, and control them in the quantum universe. So that's essentially going to be the topic. It's going to be mostly theoretical, but throughout the talk, I would also showcase some more practical usage of this theory in different situations. And since learning is going to play a very important role in the talk, I'd like to first define what I mean by learning. So for different people, learning can mean different things. Maybe it's training a neural network. Maybe it's human that's trying to learn about things. But here I'm going to consider a more abstract model. I'm going to consider learning to be a combination of the following four information manipulation process. So first, there's going to be some aspect about the universe that we would like to learn about. So it could be a quantum system. It could be a quantum dynamics. It could be even more complicated objects, such as the entire phase diagram, when we tune the Hamiltonian, what the ground state looks like, etc. So there's going to be some unknown aspect about the universe we would like to learn about. And we first have to receive information by some means. So it could be by doing experiments, by performing measurements. We then process that information using some computational model in order to form a predictive model about that unknown aspect. It could be an effective model, or we can try to learn the true underlying model. Then we will store that model either in classical memory or in the future, maybe in quantum memory, such that subsequently we can use those models to make accurate prediction in new situations, like predict what would happen if these molecules are placed in this way, predict what would happen if we try to manipulate these quantum devices in some way, etc. So it's a very abstract form, but that's the level of abstraction I'm going to be operating in. So the key motivating question of this field is to understand how we can efficiently learn in the quantum universe. So particular in this tutorial, I will be separating into two parts. The first is learning using classical machines, and the second is learning using quantum machines. So ideally, I would cut in the half in the middle, and then we will have a break. But let's see how things goes. So first, I'll be starting with learning using classical machines. So the object is quantum. We wanted to learn about the quantum world, but using classical machines. So here, when I say classical machines, I kind of meant more broadly. So it could be just a classical computer trying to understand the quantum universe. It could also be human in a way. So like scientists are kind of classical machines. Yeah. And the key question there is, what can classical machines learn about quantum systems? So we all know quantum systems are very complicated, but there are certain things that we can learn very efficiently as a classical being, and we would like to understand what are those things. And another question that's a very fundamental question in the intersection of machine learning and quantum physics is, can classical machine learning algorithm perform better than traditional non-machine learning algorithm in solving quantum problems? So these are the two main questions that I will be diving into. And for now, I will be starting with the first question. But on a more philosophical level, what we would like to really understand is how can a classical machines see quantum many-body system? So there's some quantum system, it's very complicated, there's all these entanglement, and we would like to be able to see them as a classical being. And here what we mean by seeing is the ability to convert some unknown quantum system that's generated or synthesized in a lab, turn them into some efficient classical representation, such that that classical representation, which is just a bunch of 0, 1 bits, a classical machine or a classical being can look at them and understand what it is and make prediction about different properties of the quantum system. So that's going to be the first starting question that we'll be looking at. And then afterward, we're going to build on this, like we're going to provide some answer to this question. We definitely didn't answer this question completely. There's still a lot to be explored, but we provide some initial answer to it, and then we're going to build on it. In particular, the answer to this question is essentially this classical shadow formalism that I'm going to talk about. So let's begin by reviewing some of the standard approaches for solving that question. One of the most standard approaches is called quantum state tomography, and the key idea is to learn the full representation. So we know quantum mechanics, one can formulate it as density matrices, which are just 2 to the n by 2 to the n PSD matrix with trace 1. And the goal in quantum state tomography is to learn this PSD matrix to some small error. Usually people consider trace distance. And the reason for trace distance is because trace distance, like closeness and trace distance, essentially say that no matter what kind of properties you try to predict, it's only going to be epsilon far, so it will be close. So that's one of the more standard approach. And because we're trying to learn these exponentially large metrics, it's going to scale exponentially in all kinds of resources. So here are some of the resources that people care about when trying to learn quantum system. In particular, for the sample optimal protocol, we have the following scaling. So what I mean by sample here is if you only have a single copy, a single sample of rho, then it's impossible to reconstruct the density matrix. Because you can imagine rho is essentially just a probability distribution over pure states. So if you only get a single sample, that's just like a sample from a probability distribution, then you're not going to learn the probability distribution from a single sample. So all protocol for doing quantum state tomography, almost all protocol, have to have multiple copies, multiple samples of the state rho. In particular, this protocol tried to minimize the number of samples needed. And what they showed is that the sample complexity is given as 2 to the 2n, so 4 to the n, which is essentially just the number of entries in the PSD matrix. And in order to achieve this sample optimal protocol, what they need is to be able to put all of these samples into a big quantum memory. And recall that there's 2 to the 2n samples, so if you put it into a quantum memory, that will be n times 2 to the 2n qubits. And then followed by an exponentially deep circuit in order to generate this density matrix representation. So you can see that the quantum resource scales exponentially. And then since at the end we have this exponentially large density matrix, the classical storage would also be exponential, and the classical post-processing time would also be exponential. And since people have been synthesizing and engineering systems with like hundreds of qubits, such a tomographic protocol becomes unfeasible in practice. And hence, people have been looking into a wide range of different alternatives. One of a more heuristic approach, and there's a lot of promise and excitement around it, is based on using neural networks, or more generally deep learning, in order to solve this task. It's a purely heuristic approach at the moment. And the idea is that instead of doing these very complicated circuit in order to achieve the sample optimum protocol, what if we just do some simple quantum measurements? Just do the simplest ones that we can do in the lab. And then we just try to train some machine learning model, like a neural network, to try to represent the quantum state. And there's a specific way that people do it. It's called neural network quantum state, or neural quantum state, that can be used to represent quantum systems using neural network. And what they're trying to do is they try to optimize that neural network in order to fit all the measurement data. One of the procedures is known as POVM neural network tomography by Huang Carrasquilla et al. So the nicest part about it is that the quantum resource is very, very efficient. It's just have some simple quantum circuit and then followed by measurement. However, because it's a pure heuristic approach, a lot of the other aspects are very much unknown. So like, we don't really know if the sample complexity is efficient. People see that for multiple cases, it seems to be efficient, but it's not known if in general or in what situation it would be efficient. And it could still be exponential. And for general state, it very much likely would be exponential. And since the sample complexity is unknown, the classical storage is also unknown because it depends on sample complexity. And the classical post-processing time is also unknown. And it might be very long. And since we're trying to train some neural network, that training process typically takes a long time. So even though there's a lot of excitement and a lot of research going on in this direction, it's not very convincing or not yet very convincing that this is a good approach. In particular, what one really wants. Yeah, so what they often consider is I would say it's more like they just force it to be simple, and then they just get some measurement data and then train the neural network. So some of the examples they use here are for each qubit, just randomly rotate them, like applying single qubit gate, followed by measurement. So they just say, okay, so that's what I can do, and that's a very simple quantum circuit that they consider doing, and then they just use the measurement data to train the neural network.
But just to be fair, can you also do quantum state tomography under similar assumptions? Which means you get everything.
That's a good question. So if you perform single qubit rotation, so then in that case, the sample complexity would not be 2 to the 2n, but it would be much higher. I think it's not that much higher. Oh no, I think it's quite higher. It's 3 to the n times 2 to the 2n. So there's another 3 to the n factor in front. But if you do exponential number of measurement, you can still do quantum state tomography with simple quantum circuit. It's just not the sample optimal protocol. So there is a trade-off in here. You can try to make the sample complexity bigger, and then you can use much smaller quantum resource. So
that's not very much worth it, right? Because everything's exponential anyway.
That is true, but ideally we want something. So what they found, at least in some of the paper like this, POVM neural network tomography, is that for learning many physically relevant states, you don't need exponential number of measurements, and you can already learn them. So basically what they're trying to, or what these recent approaches are trying to do is to get away with the exponential scaling. And they want it to be efficient.
If you apply this POVM, how many POVMs can you apply? Is it just once, or you probe for many of them? I mean, I give you the state, and you apply POVM. So is it? I just not know what the restrictions are, right? So.
Oh, you mean like when I say POVM neural network tomography?
Right.
What I mean.
You know how many POVMs are we allowed to apply?
Yeah. So it's okay. So there's some complication here. So first of all, like we assume that, there's rho, that's the object we try to learn. And as I stated earlier, if there's only a single sample, then we're not going to be able to learn it. So we need multiple samples. And what the sample optimum protocol do here is they perform one very big POVM that acts in an entangled way on all of them. And on the other hand, for this POVM neural network tomography, they're doing something very simple. They're just, for each, so recall that each of these rows is a bunch of qubits. So what they're doing is they say, oh, for each of these rows, maybe I just measure them. Or maybe they apply some smaller short depth circuit, and then they measure them. So that's kind of what they're looking at from a more empirical point of view. So, yeah.
So these circuits that they do to create this sample for training, isn't it limited to the state that circuit produces? So if you want to learn more complex systems and you want the neural network to generalize for that, how do they account for that?
Yeah, so you're asking like, perhaps if the system is more complicated, then the sample complexity will
Unless
have
they're
to increase.
assuming that the distribution doesn't change as the complexity of the system changes. And I don't think that's the case, right? So how do they account for that, for the distribution that changes across quantum states?
I see, I see. Yeah, so I would say right now so far what people have mostly been, so they do have some kind of empirical study. So they consider different complexity in the state, and then they try to see how the sample complexity scales and so on. So they often have some plots that says, oh, I try to increase certain aspects of the system so it becomes more and more complex, and perhaps using neural network tomography, it looks like it's growing linearly instead of exponential. And so they have some empirical study on that front. Is that what you're asking, or?
Yeah, sort of.
But I would say those are heuristics, so there's no rigorous understanding of it. So it's a little bit hard to say like what's true and what's not. And that's one of the questions we would like to address.
Also, do they have a lower bound on how much they need to sample in order to get, because one of the papers like that, like one of my papers in that, when Google was doing its quantum supremacy experiments, they did find a lower bound on how much you need to sample from the quantum system in order to get something that represents the Fourier promise.
I see. Yeah, okay. When you say lower bound, I guess you just meant they empirically can test it and see when would it become feasible, rather than theoretical lower bounds. And
it is still a theoretical lower bound, but it's sort of representative of the distribution on how many times you need to run the circuit and get the samples.
I see. But usually those lower bounds are always focused on a specific neural network. But perhaps if you use a different method, different neural network, it might have different scaling and so on. So yeah. That's kind of what I mean by not have a very good theoretical understanding. So of course you can test things empirically and you can look at things, how it scales and so on.
Could you just say a word? What is the classical version of this? I mean, we would ask the same thing, learning probability distribution, right? So what would be the scalings there if you want to learn it just by sampling or by some kind of neural network?
Yeah, that's also a good question. So when we consider the state role to be diagonal, that's a classical probability distribution. And learning classical probability distribution to small TV distance is also exponentially hard. And so in general, if you say, oh, I wanted to train an ML model to generate human faces or artworks, then if you consider in the worst case situation, then that's also exponentially hard. But in practice, you see that it's working very well. So I would say that's also one of the motivations for why people are thinking, oh, neural network can be powerful, because quantum states, in general, that's crazy. And it was very hard to learn, but perhaps neural network can still adapt to some of the structure in physical systems.
So yeah, my question is, so if learning the quantum state itself is of exponential cost, that's why now directly learning some measurements like observable from quantum state, those data should be not exponential. Maybe this can reduce the cost.
Yeah. So that's a great question, and we're going to talk about that just in a second. Okay. Is there a question there?
I was going to ask, what's the access model to the samples? Like, do you assume they already loaded into the wires of the circuit?
That's a good question. So it depends. Like here in the sample optimal protocol, they assume that all of these rows are already loaded into the device. And on the other hand, for here, they just kind of assume you already did some measurements, and now you just are analyzing the measurement data. So that's kind of different model. Okay. So hope that clarifies things. And as we can see, what we actually want is something of the following form. So we want to have a rigorous, provably efficient procedure that can learn a classical representation of some unknown n-qubit state role from few measurements. Ideally, the number of measurements doesn't need to scale exponentially in the system size n, such that afterward, we can just take that classical representation to predict many properties of the state. So this aspect is very close to say we only wanted to predict some property, instead of fully reconstructing everything. So this is more closer to what people practically would want to be able to do. And essentially, this classical shadow formalism try to provide an answer to that question. In particular, in this paper, we proved the following theorem. So let's say M is the number of property that we care about, and B is some norm bound, and epsilon is an error. What we showed in the theorem is that there exists a constructive procedure that can learn some classical representation of an unknown n-qubit state role by performing t measurements where t scales as b log m over epsilon squared, such that subsequently, given any observables O1 till m with a Frobenius norm bounded by b, the procedure will be able to use that classical representation to predict the expectation value of all of these m observables up to epsilon error with high probability. So for example, if we would like to predict 10 to the 6 different observables, all of which has a norm bounded by 1, naively what one would do is one would just measure each observable. So for each observable, you need to measure it for 1 over epsilon squared times in order to get it to epsilon error, just by averaging. And then you need to perform it for 10 to the 6 times in order to get the full thing. So it's like m over epsilon squared, that's the naive bound. On the other hand, what the theorem shows that is you can take a log in m. So if you wanted to predict 10 to the 6 different observables, even though they might not be commuting, they might be incompatible to one another, as long as they have a bounded norm, like the Frobenius norm is bounded by b, or 1 here, then we only need 6 log 10 over epsilon squared experiments. And furthermore, from the theorem statement, it's stated as 2 parts, because in the first part, when you're doing the measurement, when you're learning the representation, you don't need to know what these observables are in advance. They can be chosen later. But there's one thing to know, you cannot choose them by staring at the representation. So you create the representation, and now it's kind of hidden. And then the observables come in, and then you predict them. So that's the theorem statement.
So quick question. So in part 1, does epsilon have an independent meaning?
Sorry?
Part 1, does
Yeah.
epsilon have an independent meaning or definition? Like, for example, is it to within epsilon some norm of rho that you need so many measurements? Or the epsilon is really dictated by the second part?
Yeah, the epsilon is really dependent by the second part. So you can see from the theorem, there's no assumption about rho. Rho can really be anything. And, okay, sorry.
Oh, sorry, were you done with the
Yes,
there?
yes.
Oh, can you maybe repeat the last part that you mentioned earlier? So you can't choose the measurements adversarially looking at the classical representation, or sorry,
Yes.
what's the...
Yeah, so basically, you can imagine like after you create this representation, you stare at it, and then you look at, it looks like this, and then you adversarially construct an observable.
Okay. And it's
it will fail.
in principle classically efficient to do that if you
Sorry?
wanted. It's in principle classically efficient to do that if you wanted to from the representation.
It's not entirely clear if that's efficient, actually.
But there exists
But, yeah.
cases.
So in part 2, you say with high probability, is that probability dependent on the number of measurements, or is there even a way for me to know if I succeeded or not in getting this?
That's a good question.
Excellent.
Yeah, so with high probability, it's kind of inherent in measurements. So when you have a quantum system, when you measure it, it's inherently random. So you might just be very, very unlucky, and then perhaps the state is, for example, like the state is, let's say it's a single qubit state, it's very close to 0 state, but it's not exactly 0 state, so it's like on the Bloch sphere, it's slightly tilted. And now if you measure in a z basis, and maybe you're very unlucky and you keep getting 1, then you would think that the state is 1. So that's basically what this high probability is trying to rule out. So you can be very, very unlucky, and then you thought it's 1, but actually it's very close to 0. So it's with high probability, the probability is with respect to when you perform a measurement, there's an intrinsic randomness in it. But that scaling is very mild. So if you say we wanted to do it with 1 minus delta, like probability at least 1 minus delta, then the scaling is just log m divided by delta. So you can imagine like you just increase a little bit more, and now the failure probability is exponentially small, so you don't care about it.
If you're choosing the O's in the second part, why does their bound already appear in the complexity of the first part?
Yeah, that's a good question. So this statement have a lot of flexibility in some way. So you can imagine like you just perform T measurements, and now you start choosing these observable. Some observable have smaller norm, and some observable have bigger norm. There's a way to manipulate the theorem so that for this one that has smaller norm, you can predict to epsilon error, but one that have bigger norm, it would predict with higher error. So once you think of it as there's some scaling like that. So you can say, oh, if the same measurement T, I can make epsilon smaller, and now the norm bound B would become like also smaller. But if you make epsilon bigger, then you can handle observables with bigger norm bound. So that's kind of how one could view this theorem.
So following Dima's question earlier, the classical version of this is the Johnson index.
That's a great question. So personally, from my end, that's conceptually how I started this. But I would say Johnson-Lindström, and this has a lot of there's things that doesn't really add up. Like in Johnson-Lindström, you have vectors in very high dimensional space, a lot of them. And now it says if you perform a random projection, then now they're in a much lower dimensional space and their geometry is preserved. But here, in a way, there's only a single object rho. That's like the one object that we care about, and then we have all these observables. So I think conceptually there are similarity, but when one look at it mathematically, I think they're they're very different. Of course, they're both probabilistic and they're very sketching conceptually, but on the underlying, like for example, if you know Johnson-Lindström, I don't really know how one would be able to derive this.
Yeah, so Johnson-Lindström is like the idea, but is there a classical counterpart of this theorem?
So the classical counterpart is actually the following. There's a corresponding theorem, which is pretty easy to prove. So suppose that you say rho is just diagonal, then, which basically means it's a probability distribution, then you can prove, like this statement also holds. So I think that's the classical counterpart, which is when you take rho to be diagonal. Yes, and OI also diagonal. So rho diagonal, OI diagonal. So in that case, you should think of OI as like a function. Given a bit string, it outputs a value. So it's a function over a bit strings. And then rho is a diagonal, which is probability distribution. And actually, in that case, you can prove a stronger result, where the Frobenius norm is replaced by the spectral norm squared. Like trace of OI squared is replaced by spectral norm squared, which is stronger. So classically, there is a stronger result one can prove, and I would say that's the classical analog of the theorem. And Johnson-Lindström is like a different way of looking at it.
And what's the main complication going from the classical?
Yeah, so classical version is very simple to prove, and one of the reasons is because there's only one basis. Essentially, you just sample in that basis, and now you get this empirical data, and you have all these samples, and then you just take average. The complication in the quantum case is that there's all these different, so the idea is the following. You can think of it in the classical case, all observables, they commute. So you can simultaneously measure all of them. And so you can simultaneously predict all of them very efficiently. But in the quantum case, these observables, they might not commute. And this non-commutative plays a very big role in quantum. And that also makes the result more, like showing a result like that more challenging.
Is the classical version sort of optimal in the same way the quantum one is? Like, do the same lower bounds on this kind of procedure hold when rho is diagonal?
So when rho is diagonal, the optimal protocol is when the optimal scaling is when that trace OI squared is replaced by spectral norm squared. Okay, sure. On the other hand, for the quantum version, this trace OI squared, as I would talk a bit later, is fundamental.
So that was my other question. You're sure this is the norm, or it's not some funny operator space norm that replaces this Frobenius norm? This is optimal, right?
So when one focuses, so this is optimal.
Oh, wow.
So it doesn't work with the 4 or the 8 norm. You know it doesn't work if you replace OI2 by OI to the 16, which would be weaker, right?
When you say, I
If we
see.
know that doesn't work, then we don't have to search, right? But
I see. I think it's not. At least, so because the lower bound is more like there exists a collection of observables and a collection of states such that this b log m over epsilon squared, where b is the trace OI squared, is optimal.
yes,
So-
but do you know that the square in number 2 is optimal? Or you could work with 4 or 6 or 8.
That's a good question.
Because in the classical case, you said that you're closer to L infinity, right?
Yeah, so first of all, I know infinity norm doesn't work.
So one would
Yeah,
say
but
that
then it's the
there's a
3,
second
4, 5.
generation of your theorem where you do it with 4 and one with 6.
My suspicion is that it will not work, but I don't think there's a proper proof yet. So that's my intuition. So let's keep it that. Okay, there's no more. Oh.
One last question. So in part 2 of the theorem, the way I'm reading it right now is that if you choose the observables randomly, then this thing will hold. So I kind of want to know if you, there is a bad set for which this thing will fail, right? So I want to kind of know like how big is the good set versus the bad set? Are both of these open sets, and if it is, then I want to know how big is the bad set compared to the good set, and if not, what is if the bad set is really small, then like what is the Hausdorff dimension of these sets?
Yeah, I think that's also a good question. Let me try to think of like a way to clarify that. So another way to state the theorem is you can pick whatever set you want, O1 to OM, you pick it and fix it. And now you do the measurement, b log m over epsilon squared times. And then using the measurement data, you can predict all of them correctly. So that's a different statement. So that's the same statement, but in this angle, you can see that the observables can be chosen whatever way you want. So it's more like the following. It's like if you look at the space of the observable under the bounded norm, the space of the observable is actually doubly exponentially large. It's 2 to the 2 to the n, and that's a very big space. And if you, from that space, you pick m of them, then with high probability, you will be able to predict all of them correctly. But that space is so big, and there's going to be a lot of them that are going to be wrong for any randomness. But no matter how you choose it, they're going to be correct. So that's with high probability. So that's one way to think about it. Is that the space of observable? That's why. So it kind of goes back to the hardness here. It's really because the space of observable is so big. Like, okay. So if the space of observable is only exponentially large, then you can just take a log of it and you get a number of measurements that scales polynomially. But why is quantum state tomography scales exponentially is because the space is doubly exponentially large. So when you take a log of it, it still scales exponentially. So in that sense, if you look at in the whole space of observable, I have this classical representation. How many observables am I wrong? Most of them you're going to be wrong. But when you pick any of them without peeking at the classical representation, then the randomness help you. And for any choice, they're going to be correct with high probability. So that's kind of the more subtle picture of this.
So it doesn't matter how close the n-qubit state is to the true state of the system?
Oh, what do you mean by true state? Like there's no true state here.
So if you learn the classical representation, you get an output from it, right? That might not be exactly the same as the actual state of that system if you were to run the quantum circuit on a quantum computer, for example, that's error corrected. So does that affect your the accuracy or the probability of your observables?
Are you saying, like, suppose you run a quantum circuit and there will be an ideal state, and then, but when it's noisy, then there's a roll. Is that what you're trying to say? I see.
Because you're learning it classically, right? So you can't learn the entire 2 to the power 2n state, correct? So
Yeah, this is a efficient classical implementation, so you
yeah,
you
so
will not be
does
able to.
it matter like how close you are to the ideal state?
So as stated here, you can see that there's no mentioning of the true state. So rho can really be anything. It's any possible state. So if your ideal state is this psi, maybe rho is just completely far away. And this theorem will still works. But I guess you wanted to understand, like, if rho is supposedly close to some state, then can this theorem be improved? I think that would be a more natural question. And I would say yes. I think if you have more structure or knowledge or restriction on rho, then in general you can improve it. At least we don't have a lower bound. The lower bound assumes that rho can really be anything. So that's kind of a situation.
Can you, just for understanding this, I mean, it's a great theorem. It's just that, so you said the OI heads, they are constructed independently of the OIs, and they are also independent of rho. So I'm asking about the logic, right? I don't know what the OIs is, but you're constructing these OI heads, right?
So this OI head,
they depend
depend
rho,
on,
or they do not depend on rho. And do they depend on the big OIs, or do they not depend?
That's
That's very important, right? If
They
you can
do.
do that
So
universally.
each of these OI had, they depend on the observable OI as
And
well
rho.
as this classical representation. And the classical representation is constructed from rho, so there's definitely a dependency. Yeah.
So, sorry, will you tolerate one more question?
Yes.
Is there a relative version of this in the sense that if if you have a quantum subsystem, and instead of taking the trace, you take a partial trace onto that subsystem, and what you're allowed to measure is instead of OI hat, or instead of trace OI rho, you're actually seeing the partial trace of your observable on that subsystem. Is there a similar theorem like that?
Are you saying instead of looking at rho, I first take some partial trace, like I exclude everything that's not in. Is this or?
Yeah.
And then
so I have some observables upstairs in the big system. I take the partial traces. I take the partial traces of the observables and then I measure them, which is, I guess, the same as what you wrote.
I see. You're asking this.
Yeah.
Yeah. So this is equal to OA tensor I.
No. Sorry, what I meant to say is that suppose you're given access to trace sharp A of OI. That's something you can measure. Well,
Yes.
That's something that you're given access to.
Yes.
With that knowledge, can you reconstruct? Can you construct your
Something like this?
Yeah.
In general, no. In general, no. Yeah. Because you're already restricting your knowledge, and then if the observable has some, like if the state has some entanglement with the outside, you wanted to see that, then you're not going to be able to see.
How does this theorem play with norm equivalence? So it says that in finite dimensions all norms are equivalent, because you make a statement like with some other norm it doesn't work or something.
Yes. So, yes, it is true that in finite dimension, like constant dimension, they're all equivalent. But in general, you only have something like this. So this is the dimension. But because the dimension of the system scales exponentially, the Hilbert space scales exponentially in the system size. So that dimension, yes, it is equivalent under these dimensions, but these dimensions are very big and making them a big difference.
And I guess worse than that, this is essentially an equality up to the factor of 2 for a random O.
Right. Okay. And so now what I would like to talk about is how we establish this and what does the procedure actually looks like. So the procedure would also have two parts, same as the theorem. The first part, we take data, and then the second part, we make predictions. So in the first part, we would repeat the following for t times. Every measurement is essentially a randomized measurement. What we do is we would first sample a random Clifford circuit, UI, to evolve the system. And then what we do is we would measure that system after evolution in the computational basis. And that will, after you measure, that would just collapse the system into some bit string, n bit string, given by bi. And recall that random Clifford circuit. Not sure how familiar people are with random Clifford circuit, but random Clifford circuits are a class of quantum circuit that can be simulated efficiently on classical computer. And Furthermore, the amount of randomness in a random Clifford circuit is roughly n squared. So you sample n squared classical bits, and then you can generate this efficiently simulable Clifford circuit. And now what we would do is we would store the classical shadow. And the definition of classical shadow in this particular case, so there's a general framework for it, but in this particular case, the classical shadow would be written by this form here. So we take the UI, dagger it, invert it, apply onto BI. So Clifford circuit apply onto a computational basis state, it generates what people call stabilizer state, which is a state that can be efficiently represented on a classical computer and efficiently manipulated. So that's what these UI dagger BI would be. And then it's just multiply it by 2 to the n plus 1 minus identity. So the intuition behind this procedure is the following. So think of the quantum state as a high-dimensional object, and now we're just looking at it from a different angle. Every time we look at it using one Clifford circuit. So we have U1, look at it, now we measure, it becomes classical, that's this B1. We do it in a different way, U2, B2, U3, B3. And yeah, just to say more clearly that this sigma I hat, you can represent it efficiently on classical computer using n squared classical bits.
But this is from random angles, not like necessarily orthogonal ones like in the image.
Yeah, they're not necessarily orthogonal, like different Clifford circuit, when you think of it as some, it depends on what kind of norm you do, but if you just think of normal Hilbert-Schmidt norm, then these UI are, they might not be orthogonal. But in general, when you sample it randomly, they're mostly very orthogonal to one another. Okay, so that's the procedure. So you just perform these simple measurements. And now during the prediction phase, what we do is the following. So recall that these classical shadow, these are sigma I hat, which can be represented efficiently on classical computer. And given T of them, we would like to predict properties of the quantum state rho. And the algorithm for predicting the property is essentially a median of means estimation. So for each of these sigma I hat, we take the observable. So recall that sigma I hat is sampled from a distribution that depends on rho. Now we take the observable, take sigma I hat, and then we take their inner product to give rise to a real number xi. And then what we do in the prediction is we will chunk up all these t data points, t values, t real numbers, into k chunks. For each chunk, we average them, and then we take the median. And that's the predicted OI hat. So hopefully from this algorithm and the procedure, it becomes clear that these OI hat, how it depends on rho and O and etc.
Yeah, so in your method, how do you compute xi? Do you compute it on the classical computer?
Yeah, that's a good question. So
There's a question online, but finish the first question.
Okay. Yeah, so for various classes of observable, you can compute that efficiently, but not for all. Because in a way, these observables are also exponentially large metrics, so specifying them could be very hard. And you can also kind of hide quantum circuit into them if you try to describe them. So for various cases, you can do it efficiently, but not for all cases on the classical computer. Yeah, what was the question on the, I don't think I could see the online.
Whoever's online, speak up.
Oh, hello. I was wondering for the classical shadow, why you subtract the identity?
You mean like why is there a minus identity in the sigma I had?
Yeah.
Yeah, so that will become later. I'll dive into a bit of a proof idea for this, and then the presence of the identity will pop up. It's essentially to normalize it so that it becomes an unbiased estimator for predicting properties.
How do we choose k here? Like, does it matter?
Yeah, it's a good question too. So in the theorem, there's one way to choose k. Empirically, you try a few different k and see what kind of produces the best result, like make it more stable. But k here, theoretically, is chosen to be log m. So how many observers you want to predict, you take a log, and that's k. Okay. What happened? Oh, okay. Oh. Oh, wow.
to unmute yourself, Victor.
Yeah, please ask your question.
Yeah, please ask the question.
Yes. So it's very unusual to see a median of means estimator as an efficient estimator to do something. So I wonder if you use it because it makes the proof easier, or because you actually think that this is a procedure which is optimal in practice.
So for this random Clifford circuit approach that I talk about, I think doing median of means is required, but there are some other variants of classical shadow where you just take average is sufficient. And let me explain a little bit why median of means is needed. The problem is that you can see this classical shadow, there's a very big number that was multiplied in front. So what could happen is that you get very unlucky, and then when you take the trace, like this xi value, they can be exponentially large. So it's very, very rare, but because of this unboundedness, like xi can have a small probability of being very large. The estimate, if you just take average, can be not very robust, and one would not be able to prove the desired theorem. But taking median essentially kills all those outlier, which happens very rarely. So that's kind of the idea behind using median of means. In particular, one could also prove a theorem based on mean. And in that case, what one gets is, instead of log m, one just get m. So t becomes bm over epsilon squared. So in that case, you don't really get any saving from the naive procedure of just measuring each observables individually. So that's a situation that happens for this random Clifford circuit version of classical shadow. But there's another version which I'm also going to talk about, and for that version, you're actually taking average can be shown to be good. Okay. Yeah, so that's
Yeah, so this might be a bit of a naive question. Is the classical shadow dependent on the circuit?
Which circuit?
The formula for the classical shadow.
You mean when I'm applying the circuit UI? You mean does it depend?
Is that dependent on, is the formula dependent on the circuit that you're applying?
Yes. So this sigma I had, you can see there's UI dagger, BI UI. So.
But does the general structure of the formula stay the same if you use a different circuit, or do you still use 2n plus 1 UI?
Oh, you mean what if you use a different circuit? Like instead of Clifford circuit, you use. Yeah. So then the formula would change. And there's a general framework where you can pick whatever random ensemble, like random distribution over unitary that you wanted to apply or circuits you wanted to apply. And then there's a corresponding formula that one should use in order to do prediction.
Is that general framework in the paper?
Sorry?
Is that general framework in your paper?
Yes. I'm also going to mention it later. Okay. So now let's look into a sketch of the proof. So similar to most statistical estimation procedure, what we need to understand are these first few moments of the estimator that we are looking at. So here we call that this classical shadow sigma I had. It's a random object. It's a random matrix because UI is selected randomly, and when you perform measurement, BI would also be randomly generated. And we can first look at the first moment of this object. The formula is given here. So there's an expectation value that's taken over the unitary that we sample from. And then there's an expectation, essentially, over BI. So here I write it out as a sum, but given a UI, the probability that you see BI is given by UI roll UI dagger and then smash it with BI. And then in the middle, that's the object. That's the classical shadow object that we are looking at. So as we can see, the first moment of this classical shadow corresponds to essentially the fourth moment of this unitary UI. And in quantum computing language, we always say, because usually UI and UI dagger appears at the same time, so we kind of don't count them as twice, so we just say it's called second. Sometimes we call it second moment of UI tensor UI dagger. So that's the first moment. And then one can also look at the second moment of the classical shadow. to here, the second moment is considered to be, because it's a metric, so the second moment is the tensor product of itself. And that, if written out properly, it corresponds to the sixth moment of the random Clifford circuit. So why is that important? Because now when we understand the connection between the moments of this classical shadow and the moments of random Clifford circuit, we can then utilize this very well-developed technique called Weingarten calculus to understand it. So particular Weingarten calculus that characterizes all the moments for a random exponential sized circuit. Or another way people talk about it is a hard random unitary. So we consider the unitary group, and then we consider the uniform measure, the hard measure on it. And when we sample a unitary from that distribution, there's going to be a moment, and that moment is essentially characterized by Weingarten calculus, which says that the moments of SU 2 to the n correspond to the symmetric group. And in particular, the first moment, it would, yeah, there's a correspondence between that, which I'll talk a little bit later in a more simplified setting. And what's nice about random Clifford circuit is that it matches up with these exponential size circuit. So recall that if you have a random unitary over 2 to the n, in order to synthesize that as a circuit, that would require exponentially deep circuit, and we wanted to avoid that. But the nice thing is that random Clifford circuit, that's only linear depths, but yet it matches these exponentially deep circuit up to the sixth moment. But higher moments, it's crazy. So there's a lot, yeah, it doesn't match. And there's a lot of correction terms and so on. But up to the sixth moment, it matches exactly.
So the idea is here is a paper, is a free design,
yes.
And then you turn that into the integration on hard and with the Weingarten on hard.
Yes, yes, yes. So now, because of the first two, we have the moment, and then we connect the moment of these new object to the moment of random Clifford, and then random Clifford moment will be connected to the moment of hard measure on SU2 to the n. And then essentially through all that, one can show that the first moment is equal to the unknown state rho. So when you have this object, sigma I hat, which can be represented efficiently classically, when you average over it, infinite number of them, then it becomes the same as rho. So another way to think about this is these sigma I hat, they're kind of approximately equal to rho, but up to some random fluctuation. And now what one needs to show is that the second moment is also well controlled. So I want to say that the random fluctuation is not too big. And how to control that also, again, go through all these Weingarten calculus. And that's one of the kind of the most unclear part, because there's this very big factor that was in front of classical shadow, but somehow the moment of these random unitary is so well controlled that despite having these very big factor, they get canceled out. So now basically is the first moment matches and the second moment is controlled. So, and furthermore, the nice thing about median of mean estimator is that it doesn't care about higher moments. It only cares about the first two moments. And together we will be able to prove essentially this theorem, stating that we can predict any observable O1 to OM with bounded Frobenius norm to epsilon error using B log M over epsilon squared measurements. So that's kind of the idea, the proof sketch. I wanted to just say a few words about how these Weingarten calculus works in a very simplified setting. So usually they consider the moments of these unitary objects, but here actually we don't need to consider that. That's kind of complicated. But what we need is to look at essentially this formula here. And another way to look at it is that we have So I'm going to write the equation in a way that's very amenable to tensor network analysis. Or like it's using some tensor network way of writing the formula. But if one forget about this part and focuses only on this portion and this, then one can essentially write it down as something like this. So when I draw like this part, it's essentially taking a trace. So it's taking a trace between rho and this, and then we have this object. So are people familiar with tensor networks? Okay, then I'll just continue. And then there's a sum over, so now let's forget about the ith index. There's a sum over all of these different b. There's exponentially many of them. Seems kind of scary. And furthermore, there's an exponential factor that's lurking around here from the 2 to the n plus 1. And then we have an expectation over u. But what we're going to do is we're going to look at this object alone and consider putting expectation value over u directly at this portion of it. So while this looks a little bit messy, but one can essentially just redefine u dagger b to be u dagger b to be equal to psi. And then another way to write out this thing is that it's just 2 to the n plus 1 summing over b. I mean, in a way, this depends on b, but actually, because we are considering the unitary to be, okay, so we call that the random circuit, random Clifford circuit, correspond to hard measure. So now this is just a hard measure on the entire unitary group, and hence, no matter what it applies onto, any b, the distribution over psi would just always be the same. It's like, think of it as a sphere, and then you have a uniform distribution over the sphere, and that's the distribution over psi.
But the different sizes are independent, right?
Sorry?
The different sizes are independent. The UIs are independent, right? So when you apply them to PIs, you get independent.
That is true. That is true. But here there's linearity, so it's kind of kind of pretty easy. But why do I set that? Is because since it's now, okay, let me just write down the full thing. But now instead of taking expectation value over u, we take expectation value over psi, and then we have psi, 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 like this, rho, and one should think of this as a big tensor. So if one make the definition that consider u dagger b to be equal to psi, then this form, which neglects the I part, will be equal to this object here. And because there's no dependence on b, this summing over b just get turned into 2 to the n. So we have 2 to the n plus 1, 2 to the n with this object. And now there's also a state version of second moment. So if we have a uniform sphere, we have a uniform distribution over the block sphere for n qubit system. This thing this is like the simplest form of Weingarten calculus, but this thing is equal to I tensor I plus a swap. So it swaps the two tensor component, and the whole thing divided by 2 to the n plus 1, 2 to the n. And one can see that used by plugging this all into here. These portions just canceled out, so now we just have trace of rho plus rho. And then trace of rho is just equal to 1. So essentially what we end up with is identity plus rho. And basically, the additional identity that was there is just used to kill out the identity, this part. So that answers the question why there's an identity. It just kills up an additional portion of it. And this is like the simplest form of Weingarten calculus because it only focuses on the distribution over states rather than distribution over unitaries. But that's roughly how the first moment can be calculated. And one immediately get this claim that the first moment of the sigma I hat is equal to rho. And then the second moment is much more complicated because then we don't just deal with, so for 2 elements, the symmetric group is just identity or swap, but then for 3 elements, and there's all these different permutations, and we need to deal with all of them, but just write them out, and then bound each term would allow one to control the second moment.
So what kind of control do we have, like poly n or something?
Yeah, actually, one could just upper bound it by the Frobenius norm of an observable. But I mean, when you evaluate it on an observable, that's what one gets. So there's no n factor. So recall that all the theorem, there's no dependence on system size. So the system can be 1 qubit or 100 qubit, it doesn't matter. Yeah. So that's the rough idea for classical shadow formalism when considering random Clifford circuit. And recall that we have the theorem. So one natural question one would ask is can this be further improved? In the same paper, we proved the following statement. It says, to predict any observable where the observable's Frobenius norm is bounded by B, the epsilon error, we need at least B log M over epsilon squared measurements, which matches up asymptotically. And the way to prove that following theorem is essentially relating learning to communication. So you try to set up a communication task between Alice and Bob, where Alice would try to pick some state and then send it to Bob. And what Bob would do is Bob will use the learning procedure to extract these properties in order to decode what Alice is trying to send. And then one can analyze that communication protocol using information like quantum information theory, and then one will be able to establish the result below. However, there's a key step in the proof where in order to establish that, we need to restrict ourselves to learning using classical machine. And when one considers learning using quantum machine, there's a way to break away from this theorem. Essentially related to how one manipulate things. So in particular, the theorem holds when you consider one can perform measurements on each copy individually rather than being able to store them in a big quantum memory and apply a deep quantum circuit in order to just entangle all of them. So, and furthermore, this framework can be generalized to broader setting. We don't necessarily have to consider random Clifford circuit, but what people often consider are, say, random single qubit rotation, or in some quantum chemistry simulation, they consider Gaussian unitary, like a random Gaussian unitary in order to implement it. And in particular, for the more general case, so essentially there's a freedom in choosing the distribution. And when one changes the distribution, one changes the formula for creating classical shadow, but there's a way to do it. And furthermore, one changes the class of observables that one could predict. So instead of just having Frobenius norm, one could change it to have some other kinds of norm. And the norm is, and for that, we call it the shadow norm, and the norm is defined in this way. It's a little bit complicated, but essentially the norm just corresponds to the second moment of the sort of this classical shadow object. So for the random Clifford case, which is the one that we've been looking at so far, we sample a random Clifford circuit and measure. The corresponding norm is this Frobenius norm. And the application of these are, say, for predicting quantum fidelity. So you can think of these observable O to be a pure state psi-psi. And what this says is one will be able to predict a large number of these psi-psi efficiently. So, for example, one could say, what if the state rho is generated by a polynomial-sized quantum circuit? Then in that case, we know that for one of the observable, psi-psi, where psi is some state generated by polynomial-sized circuit, the expectation value would be close to 1, which also means that for any state generated by polynomial sized circuit, one only need to perform, so in this case, m would be 2 to the poly n, and then if you take a log of it, it would just be poly n. So for any state that's generated by a polynomial sized circuit, one can just use classical shadow to learn them from polynomial number of measurements. So that's just a direct implication of this theorem. On the other hand, one can also focus on a case when instead of implementing a deep circuit, we just say for each qubit, we randomly rotate them, and then we measure. And that would correspond to we're performing some randomized basis measurement, so randomized poly measurement. So for each qubit, we either randomly measure them in x, or measure them in z basis or y basis, and that also forms a classical shadow protocol, and one can still have the same theorem. It's just the norm is different. Now the corresponding norm will be upper bounded by in this following way. So think of the observable O as acting only on k qubit, any k qubit, and then the shadow norm can be shown to be upper bounded by 2 to the k times the spectral norm of O. So as long as the observable only acts on few qubits, then one can predict a large number of them efficiently. And this can be very useful in a lot of physical applications like estimating local Hamiltonians, reconstructing reduced density matrices in subsystems, in estimating two-point correlation function, etc.
How do you compute the variance in this case? Because you don't have the 3 design.
Yeah, so you don't have a full 3 design, but one have like local 3 design. So now it becomes a very, so you have tensor product of like small 3 designs, and then one can, instead of analyzing a big permutation, one consider each small one has permutations and analyze it that way. So that analysis is actually more complicated than the random Clifford one. Yeah. Oh, okay. Yeah, so together that gives like a general framework, which people call classical shadow formalism, which classical shadow tomography, which essentially allows classical machines to see quantum systems. So there are some quantum system, perform some random unitary, and then perform some measurements, reconstruct this classical representation, and then one can predict many properties about it. So there are several different applications that people have looked at for using classical shadow. The more direct one is for benchmarking quantum system. So because we can estimate things like quantum fidelity, and we can verify entanglement efficiently, one can use it to check if the system is performing what we want it to perform. So for example, the one to the left, that correspond to experiments where we have some many-qubit GHZ state. And then there are some errors that happens in the state. And as the error becomes bigger and bigger, that corresponds to the x-axis, the fidelity should go down linearly. And we see that using classical shadow, the fidelity does track it accurately because there's a proof for it. On the other hand, what we found in the paper when we just tried this neural network quantum state tomography, we found that it significantly overestimates the fidelity. So it predicts the prediction says, oh, the fidelity is very high, but in fact, it's actually very low. So that corresponds to some of these off points on the top. One could also use it to, say, characterize entanglement in quantum systems. So here we're comparing to a paper at Science by Bridges et al., where they provide a very specific protocol for estimating, for like checking entanglement in a quantum system. And the one on the left is using classical shadow, and we can see that our prediction is much less noisier, and that's essentially exactly the pattern that should emerge for these approximate ground state of Heisenberg model. On the other hand, using their approach, their estimation error is much higher, and then there's a lot of noise in the output. And people at Google, is there a question?
Yeah, so in the first day for the program, Scott Aronson gave a talk where he was talking about efficient verification, because right now verifying the results of the quantum circuits is, of course, very hard. It grows exponentially. And you want to be able to verify the output efficiently, even as a quantum circuit grows. Is this something that people are looking into with classical?
You mean for using classical shadow? So I would say, the verification here is a little bit different because they're trying to verify the output of an entire computation. But here it's more like learning about the state. So perhaps all you care about is just a single bit, like in the output, and they're trying to verify that that's correct. But here we're trying to verify in a way, the application of this would be verifying a state. So there are connections, but I would say it's still different.
Isn't like the output of the circuit a state though?
Yeah. But that's true. That's true. So if here, like if you estimate fidelity, then the fidelity says that the entire state is correct. But what people want in verification, maybe you just want to have the output, like a classical bit output being correct. But here, the whole quantum state needs to be correct. So that's one part that's different. And also, in general, when one wants to verify the fidelity for a very big system, that system, so there are some complications about computational complexity. So this procedure, in various cases, is computationally efficient. But if you wanted to, say, verify the output of whether the Shor's algorithm is running correctly and then it's generating the state at the end, you need to be able to simulate that whole thing. So there are some complication on.
But if the complexity of the number of observables you need is so small, you could use something like Schrodinger-Feynman, right? Because in the Schrodinger-Feynman simulation, the trade-off is memory. So if you're not simulating all the Feynman paths, and you take a very small number of that, because the complexity of this algorithm is so small, then you might be able to actually use a combination of that to verify, right?
I see. So I never seen a result like that, and I haven't thought deeply about it. That sounds like an interesting idea. I would say there are some connection between them, but oftentimes these more practical benchmarking protocol, which can already be run now, versus some of the verification protocol that uses cryptography and so on, which cannot be run now. How to kind of find a middle ground, I would say, is still an active area of research. And another application of classical shadow is in quantum chemistry. So an experiment that was done by Google is that they consider trying to prepare some, say, low energy fermionic state. And the way they do it is, in running that, like for example, using variational algorithm or some other type of algorithms, one needs to keep estimating local observables or Hamiltonians repeatedly and perhaps for many different observables. And what they have proposed is that one can replace the last part of the circuit simulation by the shadow tomography approach, and then use the output of the shadow tomography in order to estimate all these observables. So people have tried that, and I think at that time, this is one of the biggest quantum chemistry simulation done by the Google group. But more generally, when one think about this approach, one can think about it as a universal converter that takes in quantum information and turn it into some classical representation, which then enables all kinds of classical computational techniques in order to address quantum problems. In particular, I'll be talking later about how one can utilize this method to develop provably efficient algorithm for, say, classifying phases of matter and predicting ground states for a class of gap system. So I think that's it for now, and let's go for a break.